Friends, in this video, let us see how Avogadro came up with his hypothesis way back in 1811. In the year 1808, John Dalton came up with his famous atomic theory. And of all the postulates of this theory, this last one is particularly interesting because there was no basis for this postulate. All these other postulates were based on law of constant composition and law of conservation of mass. But there was no evidence or basis for this postulate. He simply assumed this postulate without providing any evidence. And he said, nature behaves in simplest ways, so this ratio must be simple whole number ratio. First, let us see what this postulate means. This means when hydrogen combines with oxygen to form water vapor, the number of hydrogen atoms that completely combine with the number of oxygen atoms to form one compound atom of water vapor are in simple whole number ratios. John Dalton called particles of compounds compound atoms. Today we call them molecules, but kindly bear with this old name for a little longer. So, in this case, he assumed that only one hydrogen atom combines with one oxygen atom to form one compound atom of water vapor. Or in other words, he assumed that in one compound atom of water vapor, there is only one hydrogen atom and one oxygen atom. In case of ammonia, he assumed that only one nitrogen atom combines with one hydrogen atom to form one compound atom of ammonia. So he again assumed that there is only one nitrogen atom and one hydrogen atom in one compound atom of ammonia. And you see, these ratios are simple whole number ratios. So John Dalton not only assumed that these ratios are simple whole number ratios, but he also assumed what that ratio is in each case without providing any evidence. See, John Dalton was measuring combining weights. What are combining weights? The weights of elements that completely combine with one another without any leftovers. He found that 1 gram of hydrogen combines completely with 8 grams of oxygen to form 9 grams of water vapor. And if you take the ratio of these combining weights, it is 1 to 8. And this is not a simple whole number ratio. Simple ratios are like 1 to 1, 1 to 2, 2 to 3, and so on. 1 to 8 is not a simple whole number ratio. Then, what evidence did he have to say that atoms combine in simple whole number ratios? None whatsoever. At the same time, a French chemist by name Joseph Gay-lussac was conducting chemical reactions between gases and he was measuring combining volumes. What are combining volumes? The volumes of different gases that completely combine with one another without any leftovers. And he found that hydrogen and oxygen combine in the ratio of 2 to 1 by volume. That is, 2 liters of hydrogen completely combines with 1 liter of oxygen. And in case of hydrogen and nitrogen, the ratio of their combining volumes is 3 to 1. That is, 3 liters of hydrogen combines with 1 liter of nitrogen. And in case of nitric oxide, the volumes of nitrogen and oxygen that combine with one another are in the ratio of 1 to 1, or 1 liter of nitrogen completely combines with 1 liter of oxygen. Now, if you look at the ratio of combining volumes, these are simple whole number ratios. And here is the statement of law of combining volumes. It says at constant temperature and pressure, the ratios of combining volumes of gases are in simple whole number ratios. And if there are any gaseous products in that reaction, then the volumes of those gaseous products are also in simple whole number ratios with these combining volumes. But the interesting thing is, this is what gay-Lussac proposed John Dalton. See, you are measuring combining weights, and by no means your combining weights are simple whole number ratios. Ratios like 1 to 8, 3 to 7, etc. are not simple whole number ratios. But you insist that atoms combine in simple whole number ratios without any evidence. But now look at my combining volumes. Their ratio is a simple whole number ratio. Maybe this is what you are looking for. But John Dalton was too stubborn to accept this argument. But an Italian chemist by name Amedeo Avogadro strongly believed that gay-Lussac was indeed right. That is, the ratio of the combining volumes of gases is equal to the ratio in which their atoms combine to form one compound atom. If you take the case of hydrogen and oxygen in the formation of water vapor, their combining volumes are in the ratio of 2 to 1. That means 2 hydrogen atoms combine with 1 oxygen atom to form one compound atom of water vapor. Or in one compound atom of water vapor, there are 2 hydrogen atoms and 1 oxygen atom. And their ratio is 2 to 1, same as the ratio of their combining volumes. Similarly, in the formation of ammonia from nitrogen and hydrogen, their combining volumes are in the ratio of 3 to 1. That means 3 hydrogen atoms combine with 1 nitrogen atom to form one compound atom of ammonia. That is, in one compound atom of ammonia, the number of hydrogen and nitrogen atoms are in the ratio of 3 to 1, same as the ratio of their combining volumes. Today we know that this is indeed correct, right? And now comes the interesting argument, and it's going to be a little bit tricky. See, this is what gay-Lussac found experimentally. That is, 2 liters of hydrogen completely combines with 1 liter of oxygen without leaving anything behind to form 2 liters of water vapor. And then gay-Lussac argued that the ratio of combining volumes is equal to the ratio in which their atoms combine to form one compound atom. That is, in this case, he thought 2 hydrogen atoms combined with 1 oxygen atom to form one compound atom, because their combining volumes are in the ratio of 2 to 1. Now comes the tricky part. If 1 oxygen atom combines with 2 hydrogen atoms to form one compound atom of water, and 1 liter of oxygen completely combines with 2 liters of hydrogen without leaving anything behind, then if there are n oxygen atoms in 1 liter of oxygen, then how many hydrogen atoms will be there in 2 liters of hydrogen? It must be 2n, right? Because the number of oxygen atoms and hydrogen atoms in these volumes must be in the ratio of 2 to 1. Otherwise, there will be some leftover if 1 oxygen atom combines with 2 hydrogen atoms to form one compound atom. It's a bit tricky, but I hope you are still with me. So, this effectively means if there are n atoms of oxygen in 1 liter of oxygen, then there must be 2n hydrogen atoms in 2 liters of hydrogen. Then if you take 1 liter of hydrogen, then how many hydrogen atoms will be there? If 2 liters has 2n atoms, 1 liter must have half of them, right? That is n hydrogen atoms. So, in 1 liter of hydrogen, there are n hydrogen atoms, and in 1 liter of oxygen there are n oxygen atoms. So one consequence of this gay-Lussac's law and this assumption is that if you take equal volumes of different gases at the same temperature and pressure, then they will have equal number of atoms. Isn't this interesting? Now Avogadro had a big problem with this statement. That is, equal volumes of gases at the same temperature and pressure contain equal number of atoms. What is that problem? If you say equal volumes have equal number of atoms, and if there are n atoms in 1 liter of oxygen, then in 2 liters of hydrogen there must be 2n atoms of hydrogen. And similarly, in the 2 liters of water vapor that is formed, there must be 2n compound atoms of water. Now look at this line. It says 2n atoms of hydrogen combine with n atoms of oxygen to form 2n compound atoms of water. Now divide all the terms in this equation with 2n. Then 2n over 2n is 1. So 1 atom of hydrogen combines with n over 2n is half atom of oxygen to form again 2n over 2n is 1. So 1 compound atom of water. Now did you notice any problem with this line? It says 1 atom of hydrogen combines with half atom of oxygen to form 1 compound atom of water. That means to make 1 compound atom of water, you have to split an oxygen atom, and Dalton doesn't like it. So you have to violate Dalton's atomic theory if you say equal volumes of different gases contain equal number of atoms at the same temperature and pressure. And many scientists of the time already liked Dalton's atomic theory. There was more and more evidence supporting the existence of atoms and indivisibility of atoms. So there is something wrong with this statement, because if this is true, then Dalton is wrong. But we are not willing to give up Dalton's atomic theory. So to overcome this difficulty, Amedeo Avogadro came up with a wonderful solution. And here is how Avogadro solved this problem. He thought Dalton was right when he said matter is ultimately composed of indivisible atoms. Nothing wrong with that statement. But that does not mean atoms can exist independently or separately. Maybe for some reason, atoms come together to form small clusters, and he called these clusters molecules. So molecule is a small cluster or group of atoms, and molecules are divisible. You can divide a molecule into its atoms if necessary. So this is the picture of hydrogen gas provided by Dalton, that is composed of separate hydrogen atoms. And this is the picture of hydrogen gas provided by Avogadro, that is composed of small groups of atoms called molecules. And Avogadro did not know the number of atoms present in each hydrogen molecule, and that is not relevant to our present discussion. So Avogadro imagined that the hydrogen and oxygen gas that we took for this reaction are composed of molecules, and these combining volumes actually indicated the ratio in which their molecules combine with one another, not their atoms. So all we have to do is replace this word atoms with molecules in the statement that we previously derived. So now it becomes equal volumes of different gases at the same temperature and pressure contain equal number of molecules, not atoms. And that is what is Avogadro's hypothesis. Now, let us rewrite this equation by replacing atoms with molecules and see how it looks. So 2n molecules of hydrogen combine with n molecules of oxygen to form 2n molecules of water vapor. Now if you divide each of these terms with 2n, we will have 1 molecule of hydrogen combines with half molecule of oxygen to form 2n over 2n is again 1 molecule of water. And we have no issues with this line because molecules can be divided into atoms. Molecules are divisible. So, problem solved. Look at how inventive Avogadro was. And this hypothesis of Avogadro was tested many times and it was found true every single time. So today we can call it a law. It is no longer a hypothesis.